Good morning, everyone. This is the Tuesday morning edition of the EasyPower Refresher series. Today we're going to talk about SmartPDC and highlight some of the tips on using the tool to make life easier for folks that have to deal with protective device coordination. What the tool does is basically simplify and automate the procedure for doing protective device coordination by setting each breaker or relay for selective coordination or optimal arc flash for instantaneous devices. In reality, it actually kind of ignores the arc flash results when it comes to doing the coordination. It has the ability to set both phase and ground protective devices and verify compliance with ANSI and NEC standards. So you can use it to eliminate faults, tripping, and costly shutdowns, stamp out mistakes, and time-consuming reviews caused by miscoordination. And as I like to say, it's great for those who only do a few coordination studies a year, and even greater for those who do a lot. In terms of those who do not do many coordination studies, it gives you an expert opinion or recommendation list of the breakers that need to be or should be addressed, and consequently it gives you someone a second opinion, if you will, or somebody to check your work when you're handling a project like that on your own. And if you're doing a lot of coordination studies, this will greatly simplify the time involved in completing the tasks, because it will highlight the exceptions for you and eliminate the need to have to spend as much time on the less complex combinations of breakers, because the reports explain specific justifications and the recommendation for each recommendation that's made. So which systems does it apply? Basically all low voltage radial systems, so 600 volts or less. It also applies to medium voltage feeders serving low voltage unit substations or transformers, including daisy chain or bifurcated units. And then it also works on all medium voltage radial feeders up to 2 relays in the series. Because it's part of the EasyPower suite, it uses the same user-friendly graphical user interface, which means there's an intuitive flow that in itself makes it easier and a time saver, because you don't have to be a power user on a day-to-day basis to be able to get protective and dependable results every time you use the tool. And it does permit the interactive simulation of breaker switching, and you'll see because it works in conjunction with the power protector module, there is an interactive ability to see what the impact is on arc flash as we're doing the adjustment and coordination procedures. So let me jump into an example on the tool, and we'll cover some ground. All right, so as I mentioned before, the primary place that we see the most effect is where you need to do coordination, and that is to say the SmartPDC tool will not work with EasySolve because it doesn't have the ability to do coordination. So all I have to do is get the right. All right, in database, you'll see that we quite literally start with the same database that we use for short circuit or arc flash calculations. And as we complete our short circuit focus, or we move to short circuit focus, you'll see we have no errors in the system. There has to be some settings in the breaker description. As we go back and look at these, you'll see that on each case, we have some phase settings. If nothing, or if we haven't selected plot TCC, then the auto SmartPDC cannot obviously interact with that particular device. So each of the devices need to have this plot TCC checked. Then as we go to short circuit focus and fault the buses, we see that we have branch current in all the right places and on some order of magnitude that's acceptable. And by looking at the incident energy calculations, you can see that we really, in this particular case, we'll only have a couple buses that seem to be out of line, and that may or may not have anything to do with coordination, whereas what we want to do primarily is coordinate the largest load with the upstream breaker chain, and that works on the assumption that the downstream loads, if they're coordinated for their specific breaker, will fall into line with the upstream coordination. Now again, the tool works in conjunction with the power protector or coordination module from EasyPower, which is part of the EasyPower Arc Flash suites. So to start the process, we go to the coordination focus and we highlight a bus, in this case an MCC, and the upstream breaker. Now, an MCC, the coordination will work in conjunction with the MCC breakers if they've been designated as having TCCs. So if we're going to look at the description, here's a motor with TCC, so consequently the parameters of this particular molded case circuit breaker will be plotted on our coordination curves, and in this case we don't have a main breaker shown upstream for this bus, so what we will plot when we get to the TCC curve is that breaker on the row 1 and then the breaker here that we're going to be coordinating against, at least in the first step. So as I left click and drag to select those 3 devices, we're going to plot the TC curve, and so now it's exactly what we see here is first of all, this is the row 1 breaker, the molded case circuit breaker. Here's the feeder breaker that we have coming into switchgear 2F, and here's the motor starting curve that we want to coordinate against. Now the settings, as we look at SmartPDC, the settings are set up under SmartPDC options, and these basically outline the rules that permit us to work in conjunction or tune the SmartPDC module. So for starters, if we haven't put any protective device data, then we have the ability to choose it to exclude that particular device during the process, cancel it and do something else, or prompt to skip and cancel. So obviously if we don't have any data for a particular breaker, then it can't be included in the automated process. Here are the percentage guard bands that are recommended by NEC, and they are what are being used in the tool under supervised and unsupervised categories, and these can be adjusted and comply with the solid state trip units. The lines that we're comparing, you'll see we have cables plotted on the TC curve, and they are taken into consideration when we're setting the automated protection devices. And in terms of setting the default for the relays, you can see that we can set up per code, set up per specific demand or percentage of whatever the load that's currently connected. And this is true in case of setting up any of the devices. We have the ability to tune how the tool reacts to the case. When we're looking at capacitors, we want to consider a minimum gap between inrush and the relay settings. Likewise for motors, these are the tolerances when comparing to trip curves. And fuses, the relay default settings that can be adjusted, and the spacing that's required between the minimum time gaps for relay settings. And then all this can be carried forward in the reporting structure. All right, so then for starters, what we have currently is the MCC selected as the panel. As we fault this particular bus and plot the curve we see two curves plotted here. I want to fault this particular bus. And looking at the branch currents, we can insert the arcing current, and I selected the lower downstream breaker, which is row 1, and what the tool is telling me is that's not being used in calculating the incident, or the incident energy for this particular bus, which only makes sense because we're faulting the bus, and this particular breaker is downstream of that bus. So now we're going to look at the arc current that's being used in calculating this energy, and as we look at it, we can see that this energy is being controlled by this particular current and the set points on this upstream breaker. Now, as far as the differences between those two buses or trip points, if in fact this type of fault were to be handled or occur downstream, then we could see that at this particular setting, which would be the arcing current that's being used for this calculations, if the fault were a function of the downstream, at any rate, this shows us the ability to see the difference between the two breaker settings, not necessarily applicable in what we're just talking about. All right, so the process of doing auto coordination now is a function of making adjustments to allow for the trip or the startup current in the motor, the protective current that's required for bus faults, and then we mentioned earlier that we have a couple of cables that are in the circuit that's been selected. One is the cable run from the MCC to the motor, and the other one is this cable up here, C3B. So as we invoke SmartPDC, we can see that the recommendations are for the breaker on row 1 to be adjusted to accommodate the starting curve, and then the settings on BL2FB have to be adjusted to accommodate that daylight room to the lower breaker. Again, if we're anticipating a fault in the motor. All right, so the thing to look at that point is my report. So the auto coordination report now tells us basically for this breaker what was considered and what it has to coordinate with and the suggested settings for that particular breaker. So we have the row 1 breaker of the MCC and BL2FB, and these are the new settings, the old and the new settings as part of the recommendation. Now, and so that's a basic single downstream feeder. We can do the same thing. Let's come back over here and look at the loads on this side where we want to coordinate this. The motor's not a bus. So at this point, if we wanted to consider a fault on the motor, we might have to be a little bit clever and do something like this, where we disconnect the motor, we put in a bus so we can fault it, and so at this point I have some reason to label the motor connection at the MCC, and I wanted to know what the fault, what the coordination is between the row 1 breaker, or the breaker that's used for the motor, and the main breaker on the MCC. So we do the same thing. We go to coordination. Let's fault this bus. Let's look at the current. Let's go ahead and plot these curves. And now as we fault this bus and apply the arcing current, now we do see that the arcing current falls, interestingly enough, in actually the good area, if you will, for the downstream breaker, but in the suspicious area for the feeder breaker up on switchgear 2A, which is to say there's going to be a lot longer delay potentially at that particular current. So let's see what our difference calculator is and what it would be at the fault current. So the minimum separation here is 300 milliseconds, but in fact the breaker can't be counted on clearing on upstream until something like, well, this is it right here. This is what's coming outside of 300 milliseconds. All right. As we go in and invoke SmartPDC, let's see what the recommendations are for coordination of these devices. And you'll see that the tool took that into account, whereas we had a very long separation, or the potential for a very high high delay or high gap between the two breakers. And at the arcing current, if we're considering that downstream bus, it made an adjustment so that we have a minimal delay between them. And this is what will be shown now in our auto coordination report. So very simply, the system could be looked at as doing a first pass auto coordination, and then the engineer reviewing what the recommendations are and applying most productive time to resolving the errors or warnings that the tool indicates, rather than going through the whole process for every breaker in the system. Obviously, you want to check every breaker, but at the same time, that's having the tool go through the initial steps for you would give you specific verification that that's the place. So now that we've coordinated these two breakers, again, the MCC and the upstream breaker, the next step would then be to coordinate the upstream devices, and I'm going to go ahead and include the relay. And let's plot this. And so now we're going to coordinate. We're not going to change this relay because it's already been set, but we're going to coordinate the fuse, switch, and the relay above it. And as we look at this, I'm going to expand this a little bit, and we're going to fault our buses here and look at incident energy. We can see what's controlling the incident energy calculations. First of all, this particular bus, let's go ahead and see where the arcing current is. As I tried to look at BL2A, which is this breaker down here, we can see that it's not the controlling factor. By this error report from the tools telling me cannot calculate the arcing current, that means that this device, the breaker BL2A, isn't the device used in calculating incident energy for that particular bus. Makes me think that just looking at the curves that the relay in fact is a more limiting factor. So let's see if we can try this again. It's not going to let me do it. So one way to verify that is by selecting this breaker. There it is. So by selecting the relay curve, you can see that now I'm seeing the arcing current 85% is being used for calculating the incident energy, but it's being overridden by the effects of the relay. So at the very least, there needs to be some adjustments here, and offhand I would say is, you see as I move the relay curve, and I got it kind of out of whack here. As I move the curve, you can see it changes the incident energy being calculated for that bus. Look at the incident energy here as I change the settings on the curve. Okay, so that's an indication of miscoordination. So based upon what we selected, let's go ahead and apply SmartPDC. And you can see that we've now raised the curve, or it's recommended that we increase the relay to protect the transformers and basically separate between the breaker settings and the relay settings for coordination. So I'm going to fault this bus again, come in here and look at my arcing tick mark. It's right here. And now if I select this curve, hold down Shift and select the relay, and then produce a difference calculator, I can see that my settings, my difference between the relay and the curve at the arcing current is just under 2 seconds. So then the next question is, where is the fuse in all this? The fuse switch, which is right here. And the tool, obviously, SmartPDC can't make adjustments to the fuse, but it can show us the effect of using a different fuse. So what this is showing is the fuse operations is too slow to be a deterrent or a protective device for arc flash, and it's obviously in the circuit for protecting higher current for longer periods of time. So let's look at the report and see what it's telling us. So again, it starts with the breaker downstream. It shows us what the breaker coordination parameters we're looking at and the recommended settings, both old and new, and the reasons that it chose them. Then we look at the fuse settings for as for the fuse and why it wasn't as productive or applicable as we were expecting. And then the set points for the relays and the adjustments that were made and justification for doing that. Now, again, these are recommendations. They're not the final word on the report that the engineer makes, but they'll save time and allow the engineer basically a place to start when looking at protective device coordination. Likewise, the system can handle a whole subsystem as far as making the recommendations or invoking the tool. Obviously, it's almost impossible to tell what's going on from the visual display, but by applying SmartPDC and then looking at the recommendations now for my subsystem, my engineer can spend his time working with the exceptions rather than going through the tedium of verifying each breaker adjustment. And in some cases, there's no adjustment required for certain settings. All right, so that's SmartPDC and the value that can be gleaned from it. And certainly if you've got questions, you're welcome to contact us, tech support at easypower.com. My name is Jim. You're welcome to send me an email, and look forward to talking to you down the road. Thank you very much for attending.